So another reversal mechanism. Again, I encourage you as we go through these reaction mechanisms to consider as a review, kind of going back through and seeing the logic for the order that they're in and seeing how they're related to one another and so forth. We'll do that at the very end again, but it's a good way to sort of review kind of big picture things with mechanism, because again, you're always going to see a reaction mechanism on an exam that's not one that you've seen. So the idea is to not memorize these reaction mechanisms straight up. It's to be able to apply what you've learned to a new situation. So again, taking this Schiff base that we formed in reaction mechanism 16 and then essentially decomposing it back down to the primary amine and ketone that it originated from, we're basically going to be reversing reaction mechanism 16. So again, look for parallels to things that we've seen before. So again, taking ketals and moving them back down to ketones, which were reaction mechanisms 11 and 13, basically have a lot of parallels to what we're going to see here. I'm not going to redraw those mechanisms. I encourage you to kind of do so that you can see the parallels and the relationships. And again, one of the things that we're going to highlight in this mechanism is we're going to begin to think about how we can simplify steps, especially when we think about proton transfer steps. Making our mechanisms a little bit simpler now that we know how to do them a little bit better. Just again, another highlight of the importance of avoiding intramolecular proton transfers unless you have a sterically feasible situation. Again, forming a 5 or a 6 membered ring. You'll never go wrong with using solvent to protonate or deprotonate. That probably is a good rule of thumb to go with that unless there's some other reason to consider another mechanism. Again, I'm only going to kind of show one mechanism here where I'm going to actually draw out some individual steps, but we'll talk about how we could kind of combine them together. So, mechanism here. So we have our Schiff base from our previous mechanism. So let's draw out our Schiff base. And what essentially we're going to do is we are going to be eliminating this primary amine, which is unique that we have 2 bonds now that we need to get rid of, a pi bond and a sigma bond. And we're going to be reforming a carbonyl at this carbon, which means we essentially have to have water that comes in to facilitate this process. So like we've seen with lots of our mechanisms, the first thing we're going to do is we're going to take something that we want to be a leaving group and make it into a better leaving group by protonation. So protonation of our Schiff base here, so let's highlight this was a Schiff base. Protonation of our Schiff base here is going to generate a protonated Schiff base, which was the penultimate step that we had at the end of our last mechanism. Now we've made an intermediate that is quite electrophilic. Remember, we highlighted in our last mechanism, despite it being very electrophilic, we actually got rid of that by deprotonating here to generate our neutral intermediate, or our neutral final product here. So what we're going to see now is nucleophilic attack by our water on this very electrophilic intermediate here, generating an intermediate that's going to need to have some proton rearranging in order to move towards our final product. All right, so here again is a species we're going to have to do some more proton rearranging with. So deprotonation up here so that this guy is no longer the good leaving group, and protonation down here to make the amine be the good leaving group that we want it to be. All right, so now we have an intermediate here that when we decompose and regenerate our carbonyl here, we have a good leaving group. So we're going to generate our primary amine. And then our protonated ketone. Base easily comes in here, deprotonates, and generates our final ketone product. So again, highlighting, one of the things that could happen together. Ultimately, this nucleophile could be deprotonated on its way in. So we could combine this deprotonation and nucleophilic attack in the same step, really showing sort of an arrow coming in here and then allowing these electrons to come through and do this protonation. Similarly, we could have drawn this arrow, not going to be a lone pair on this nitrogen, but coming out and grabbing this hydrogen here. So let's change color here just so we could kind of highlight here. I'm just going to kind of draw this out here, just this one step that we have here, just to sort of show how we could combine chemistries here. So I'm going to combine sort of the nucleophilic attack parts that happen here with the deprotonation of our incoming nucleophile and the protonation here all in one step. So I'm going to draw that base here and then this general acid here. All right. So again, I'm going to do this mechanism a little bit more slowly so we can see how all of these are being combined into the same step. So we're going to deprotonate our nucleophile while it's on the way in, and rather than taking these electrons and moving them onto this and generating hydroxide, which is not reasonable, we're not going to deprotonate water. That's not going to be reasonable in this sort of environment. We're going to take these electrons and use them to nucleophilically attack here. Rather than taking these electrons and putting them on this nitrogen, they're going to immediately reach out and grab that proton, and then those electrons go here. At the end of the day, this chemistry is going to be what gets us to this intermediate in one step rather than two. So again, if you drew everything out here as we sort of have with our black color here, that would be fine. Or if you wanted to combine these two steps together here, that's sort of this kind of combining chemistries that we're interested in. So a couple of other comments though, in general, protonation and deprotonation steps are acceptable to combine with chemistry, such as we showed there with the blue sort of text. Again, but we generally don't want to combine chemistries which represent separate chemical steps. So again, we want to see this production of stable intermediates. So I'm going to highlight sort of two examples here, and again, highlighting these are things that we don't want to see. So again, we might visualize when we consider the addition of an amine to an activated carbonyl. That is what we saw in reaction mechanism 3. I'm going to kind of highlight what I mean here. There's sometimes things that you might see these getting done on the board or something like that as we are sort of strategizing what's going on, but I want to make sure to highlight that this is not a viable mechanism. So we might say, okay, we've got nucleophilic attack here on this electrophilic carbonyl carbon. We generate a tetrahedral intermediate. That tetrahedral intermediate decomposes, and then we've got departure of a good leaving group. Okay, and that goes and we generate our good leaving group plus our product here. So again, this is really good for visualizing. So it's visualization, but that is not a mechanism. So sometimes we might do this as a way to think about what's going on, but again, highlighting this is not a mechanism. We've combined too many steps. So something else again to think about is, and we've mentioned this before, we don't want to have intermediates that have charged species that would be unlikely to sort of exist in solution. So this is one that we've seen before, sort of related to this mechanism. What happened here is, even though it looks like it would be really nice to have that lone pair of electrons kind of come down there, our leaving group then leave, and when we just immediately generate our ketone, not a protonated ketone, and then our primary amine, the idea is that this was deprotonated too early. So I'm going to flip back just for a second to show our mechanism here. We're representing this step right here. So what this is trying to sort of show is, well, let's deprotonate this guy first, generate a negative charge there, and then do the chemistry. But remember how we talked about we're unlikely to have positive and negative species kind of within the same molecule? Unless their pKa's dictate that. So again, better to have a protonated ketone that you have as a product, or again, if you wanted, let me just highlight this with our blue here. If you wanted, you could have this step sort of come up here, and you could have that deprotonation happen at the same time that you're having those electrons come down to reform your carbonyl containing compound. That's acceptable, but we wouldn't want to have that deprotonation happen and then be left with this charged alkoxy group here. That's not viable in a situation where we would also have this protonated amine. So again, just a little biochemical application here. Schiff base formation is a really important aspect of some enzyme chemistries that we'll see. We generate this electron sink, which allows us to withdraw electron density both inductively and via resonance. And so that's going to allow us to facilitate some chemistries where we generate a negative charge on an intermediate. So again, we're stabilizing negative charges that are going to develop in some processes. But we need to be able to return our enzyme back to its active state. So again, if you can imagine that we've got this lysine residue almost serving as an arm that's sort of coming in, generating the Schiff base, making this electron sink that allows us to do chemistry, unless we allow that lysine to sort of let go and come back to its primary amine state, detaching itself from, I shouldn't say detaching from the enzyme, it should be detaching from the substrate. Our enzyme's not going to be able to do any additional chemistry because its arm is going to be tied up with the substrate. So again, it kind of comes in, binds to the substrate, covalently sort of attaching to the substrate to generate this electron sink. And then at the end of the day, we have to be able to release that so that that enzyme can continue to do chemistry on a new substrate. So all of these things, again, are going to find homes. All of these reaction mechanisms will find homes as we begin to study different processes of metabolism.